going to talk about boiling and condensation. So that's a new chapter. The chapter on heat exchangers is completed. Boiling and condensation are phase change processes, and along with the heat transfer, there is a phase change taking place for the fluid involved in the heat transfer process. In a way, this is also a convective heat transfer, but whatever we discussed till this point, there was no phase change of the fluid, but here there is a phase change. Because of the heat supply or heat rejection, the phase of the fluid changes. And this actually makes a big difference in the heat transfer phenomena, because there is a boiling involved where the change of liquid phase to vapor phase is taking place, and the opposite for the condensation. And so the mechanism is, though there is a bulk motion of the fluid, so we can always call it convective heat transfer, but boiling heat transfer and condensation heat transfer, they are a bit different from the sensible, only sensible heat transfer that is taking place in regular convective heat transfer phenomena. And this mechanism actually produces lot of turbulence most of the times. And because of that, the heat transfer coefficients are related with boiling and condensation are normally very high. So whenever feasible, it may be a good idea to involve boiling and condensation mechanisms to enhance the heat transfer rate. So let us understand the physics and the physical phenomena taking place in boiling first. Now, first of all, it may be important to understand the difference between evaporation and condensation. Okay. So here I am taking help of the book by Yunus Sengel. So the almost a whole chapter will be based on the contents presented in this book. So first, it may be important to understand the difference between evaporation and condensation. Sorry, evaporation and boiling. So somebody may ask you, when you put the wet clothes in open, uh, even if the water temperature does not reach the boiling temperature, that is 100 degrees Celsius, how do they get dried? So the answer to that is there is no boiling taking place. There is evaporation taking place. And that is actually convective mass transfer. So if you recall the example that we did for the evaporation of the surface of a swimming pool, right? So the swimming pool water is at a temperature obviously lower than the boiling temperature at atmospheric pressure, that is 100 degrees Celsius, but still there is mass transfer of the water vapor from the liquid into the air. And what is the driving force there? The driving force there is the concentration difference of water vapor between the surface, the first layer of air in contact with the pool of liquid or water, and the concentration of water vapor in free stream of air. So the difference in other words, you can also call it a difference of water vapor pressure between the free stream and the first layer in contact with the water surface, okay, which is going to be the saturation condition. So the evaporation takes place between the liquid surface and air or gas, while boiling takes place generally at the interface of solid and liquid. So as you can see in the figure here on the left hand side, a glass is shown and water is there in the glass, and it's shown to be at 20 degrees Celsius. It can be 30, 35 degrees Celsius, but there is still evaporation taking place. Of course, higher the temperature, higher would be the evaporation rate of water from the free surface of water into air. So that's evaporation. But boiling, as you can see, that a kettle is shown and it is put, let's say, on a gas stove, and heat is supplied to the yeah. So that the heat, the bottom surface or the upper surface of the bottom, which is in contact with water, gets heated up, and water is shown to be at 100 degrees Celsius. So ultimately, water has to reach 100 degrees Celsius so that the real boiling can start. And this surface is actually at a temperature higher than 100 degrees Celsius, right? You may not show the lid, and so the basically the pressure, you may assume that it is near atmospheric pressure. Yes, they have shown this mouth open, so that will maintain the pressure near atmospheric pressure. So the water will start boiling at around 100 degrees Celsius, and this where is it initiated? So actually the vapor bubbles, the steam bubbles are generated at the upper surface of the bottom surface of the vessel, and they get detached, and they many times pass through the water pool and come out of that, right? And the steam is escaping. So that's the boiling phenomena. Okay, so you should be able to differentiate between evaporation and boiling. So for boiling, it is necessary to for the fluid to reach the saturation temperature, right? Of course, there is something called um, uh, like subcooled boiling also, but in that case, generally the bubbles are not able to come out of the pool of the liquid, and they basically heat the remaining pool of the liquid. And we are going to talk about that also. Okay, so there has to be a difference. What is the driving potential? Again, it's the temperature difference between the surface and water pool. So the surface temperature has to be higher than the water temperature. Only then there will be net heat transfer into water, and it results in this case into boiling. Okay. So that temperature difference is called excess temperature, right? Delta T suffix E. That is the excess temperature. That is the surface temperature minus the saturation temperature of the liquid at given pressure. So delta TE is the driving force in case of boiling. Okay. So boiling, as it was explained, occurs at solid liquid interface, and here there is another example of boiling shown. It may be done, you can see here that there is a heater element inserted into a pool of liquid, water filled up in a vessel, and this is the heater, and this heater temperature is higher than 100 degrees Celsius. The system is at 1 atmospheric pressure. The heater surface, it is shown that it is at 110 degrees Celsius, and the bubbles are generated at the surface, and they get detached, and they are able to come out of the free surface, and you can see a lot of turbulence getting generated. Okay, so this is also boiling, and as it will be defined, this is called pool boiling. Okay, so you can see the basic formula here, Q dot boiling, you may write capital Q, Q dot boiling. So what would be the unit? Okay, so here it is because it is heat flux, you may write lowercase. So that's Q dot small q, so it's watt per meter square is equal to H into Ts minus T saturation. So that is H into delta T excess. Right, so that surface temperature minus saturation temperature. So in this case, it is 110 minus 100. So 10 degree Celsius or 10 Kelvin is the excess temperature, and H is the heat transfer coefficient related with this boiling phenomena. Now there are some different properties as well as uh, uh, like other physical parameters which are affecting the heat transfer phenomena. The regular thermophysical properties of the fluid, like the density, viscosity, thermal conductivity, and heat capacity, play a role here also. But there are some additional properties of the fluid which are also playing a role in the boiling heat transfer phenomena, and they are: one, the latent heat of vaporization, HFG, right? What you see from steam table, Hg minus Hf. So latent heat of vaporization also plays a role in this phenomena, and also the surface tension, because the growth of bubble is affected by the surface tension effect. So you will see that, of course, again, this is a very complicated phenomena, understanding the physics of the phenomena, and again, putting it in terms of mathematical equations is really big task. Even if it is done, solving it is again another huge task. So many times we depend upon the, or rather most of the times we depend upon the experiments done by the researchers. So we have the empirical correlations, and with the help of those empirical correlations, we try to get estimate of the heat transfer coefficient involved in the given boiling heat transfer phenomena. Bubbles owe their existence to surface tension K sigma at the liquid vapor interface due to attraction force on molecules at the interface towards liquid phase. If there is no surface tension, then there won't be formation of bubble. Okay, there won't be any formation of the bubble. The surface tension decreases with increasing temperature and becomes zero at critical temperature, right? So at critical temperature, beyond critical temperature, there is nothing like boiling. The conversion may not be actually called from liquid to vapor. Actually, you may not also be able to distinguish between liquid and vapor when you are dealing with the supercritical pressures. The boiling process in practice do not occur under equilibrium conditions, and normally the bubbles are not in thermodynamic equilibrium with surrounding liquid. Okay. The pressure difference between the liquid and the vapor is balanced by the surface tension. Okay. So vapor pressure, like the when the bubble is formed, there is some vapor pressure which is created by the vapor. On the other hand, liquid is also creating a pressure, and the surface tension is the one which is balancing those two. And when the pressure exerted by vapor increases, the one which is exerted by liquid, it get detached, and it may also burst if the size is small enough inside the liquid. Okay. So as I mentioned the word, and like the boiling that was shown in that vessel is pool boiling. Now what is this pool boiling? From name you can get some idea. There is a pool of liquid, right? When you say pool, then it means that the liquid as a whole mass is not moving, it's not flowing, right? So if you stop boiling, then it's a stagnant, in a way it's stagnant liquid in some vessel, right? Okay. So that's pool boiling. So there is a pool of water and you are involving boiling phenomena in that. So that is pool boiling. But another example or another phenomena in case of boiling can even be flow boiling. So here there is a net flow of the liquid occurring. Okay. And there is boiling. So can somebody give me examples, one of pool boiling and two of flow boiling? Okay, you can type in your answers. In your day-to-day life, or when you move around in some engineering like engineering system around you, you see it can be a day-to-day phenomena, or it can be some engineering system around you where you find this pool boiling or flow boiling, right? So can you tell me at least one example each? So water in kettle is pool boiling, right? Oh, okay, good. Okay, so that's what was shown in the example, and the water is filled up in kettle. So it's a, when you don't involve boiling, it is a pool, right? It is stagnant liquid, and then you start supplying heat, and it becomes pool boiling. And then Krupal Singh tells that solar water heater is a flow boiling. Solar water heater is not flow boiling. If you are generating steam, then it would certainly become flow boiling, right? Otherwise, it is convective heat transfer, which is taking place, which can be natural convective or it can be forced convective, depending upon whether there is a pump or not. So flow in boiler. So that's right. You might have written flow in boiler tubes, right? Then I think that would be a perfect answer. So we were pumping the water through the boiler tubes. Let's say it is a water tube boiler, and the flue gases are supplying heat to it, and it starts boiling there inside the tubes. So in that case, there is a flow, net flow, because there is a pump which is pumping it into, let's say, that drum, steam drum, and there is boiling also taking place in that, right? So steam in steam pipe, yes, but you should not say steam. Then if you say steam, then it has already become vapor, right? So water boiling in uh, pipe, right? So I think boiler tubes would be that would be the better phrase, formation of answer. Flow boiling, water in pipe boilers, yes, correct. Flow boiling. Uh, okay. Flow in heat exchanger, flow boiling. Okay. But which heat exchanger, right? You should name the heat exchanger, because heat exchanger is a general term. Okay. There can be so many different types of heat exchangers, not just in industry but around you. Shell and tube is okay, but I told you that the systems that you see around you, okay, so that you can relate the things, right? You can relate the things to what you see around you. So which heat exchanger do you see around you? Of course, boiler is a good example, which is a very common in engineering applications, but in day-to-day life also you see these heat exchangers, and where this flow boiling is occurring. So is it there in the refrigeration system? Right, you have evaporator and condenser in air conditioner or refrigerator, right? So that's an example of, okay, that's an example of flow boiling, right? So the evaporator coil that is there inside the room, right, there is a boiling of refrigerant occurring. inside the tube. Of course, you can't see it, but you call it a evaporator, but actually it's boiling, not evaporation. And then condenser outside. So there is a conversion from vapor to liquid by rejecting heat to air, and the refrigerant is condensing there. Right? Okay. So pool boiling and flow boiling, you understand the difference between the two. And our initial discussion will start with pool boiling, because flow boiling is even further complicated phenomena. Now, when you talk about pool boiling or even flow boiling, there can be subcooled boiling or saturated boiling. Right? Though saturated boiling is more common, when will this subcooled boiling occur? Boiling is said to be subcooled or local. Okay. When the temperature of the main body of the liquid is below the saturation temperature, that is, the bulk of the liquid is subcooled. So as you can see here, initially when your water was, let's say, at 30 degrees Celsius, and you started supplying heat to the vessel, right? So surface temperature would quickly rise because you are supplying a very high flux of heat from here. So surface temperature would exceed 100 degrees Celsius. Here it is shown that it has reached 107, but still the whole body, because of its mass, has not reached 100 degrees Celsius. Okay, so there is a heat transfer continuous taking place, natural convective heat transfer, as well as locally the water temperature may reach beyond 100 degrees Celsius and bubbles are generated. But what you find is that those bubbles are generally not able to go out of the pool. What happens is that those bubbles get detached, but then they break inside this pool, finally giving away its heat of condensation to this water body. Right. So when the water temperature has still not reached its saturation temperature, you may still see the generation of bubbles, but it will not result into those the vapor in the bubble coming up to the surface and going into free air, right? That they will break inside, and they will end up giving heat to the liquid, and this way this liquid gets sensibly heated very fast. Okay. But when, like, slowly the water whole body will reach at the saturation temperature, and then the saturated boiling will start, and at that time there are more number of bubbles generated, the sizes can be larger, and they are able to come up to the surface, and they burst at the surface and give out water vapor into the air. So that's the difference between subcooled boiling and saturated boiling. Most of the times when we talk about boiling, we will be talking about the saturated boiling. Okay, so now let's focus on the pool boiling, and particularly, of course, it will start with subcooled boiling, and then it will discuss about the saturated boiling. So the pool boiling most of the times is discussed with the help of a curve called boiling curve. Okay. And that will be presented, and how this curve is uh, drawn, and what is it conveyed by that curve will also be explained now. And with the help of that curve, we are able to define various boiling regimes, and we will give proper name to those regimes, and they are actually distinct to from one another because of the characteristic of the physical phenomena that is occurring. Okay. Uh, yeah. Now the surface temperature. So this boiling curve basically shows the effect of T excess on the type of boiling or the boiling regimes. Right. So if your surface temperature is low, then you may be in a particular boiling regime. If you increase that temperature, the temperature difference between the fluid and the surface, then the boiling regime may be different. Okay. As you can see here, here first thing shown is natural convection boiling. Then here it is shown, like here the temperature difference is just 3 degrees Celsius. Okay, so that is not enough to sustain the sustain and make the generation of bubbles and the boiling phenomena. So mainly it's natural convection boiling, kind of sensible heating of the liquid taking place and natural convection currents taking place. Then the next step, like when the temperature is 110 degrees Celsius. Okay, so actually you may not think it as like as you go on supplying heat, the temperature is changing, right? It may be that you are able to maintain 103 degrees Celsius here. Then this is what you see. So each system may be seen as a different system from the other system. So here is a system where you are maintaining the temperature of the surface at 103. Then you may not see many bubbles, but still there is a heat transfer, which is mainly due to the natural convective heat transfer, natural convective currents setting up and heating up the body of water. Then when you see 110, then you are able to see that it's called nucleate boiling, right? Nucleate boiling. So the bubble sizes may not be very big, and they don't cover a large area of the surface, and at that time it is nucleate boiling. You must have heard nucleate boiling even in the discussions about the boiler in power plants, right? The fire wall, that is the water wall that is made in case of the subcritical power plants. So there it is nucleate boiling which is taking place. So the surface that is covered by the bubbles, which is basically vapor, is not very big. It may be just 5%, 10% or something, right? So that at that time the type of boiling involved is nucleate boiling. Now, if you have very high excess temperature, here it is shown to be 180 minus 100, so 80 degrees Celsius excess temperature. So what is shown is that this is actually called transition boiling. What you see in this type of boiling is the in a way you can say the bubbles grow in big size, grow to big size. So actually it may not be individual bubble also, but multiple bubbles are able to join together and create a large vapor pocket, as they have as it is written. And such big vapor pockets are generated, and you can see they cover substantial portion of the surface, right? And this may not be actually very steady thing, but a very dynamic thing. That is what you see, like vapor pockets here may be replaced with water, and then again there will be vapor pocket, and again the size and the shape, etc., may be different at all different places, right? So that's a very dynamic thing. You can consider it to be just a still or photograph taken at one particular moment. But like if you take a video, then you will see that this is continuously changing. It's a very dynamic phenomena, right? And at some point you see that there is a continuous vapor. The heat supply rate is so high that the like the bubbles rising are not enough, and the what when the bubble detaches and rises up, what liquid takes its place, right? But the bubble generation and joining of those bubbles is so fast that there is a continuous uh, uh, continuous generate rather there is a steady film that is able to remain in contact with the surface, vapor film. So that's film, that's called film boiling. So these are the different regimes, and they are due to the different excess temperatures. As I told, you should not consider, you should not think it as, let's say I've started supplying the heat, so it reached 110 and then it increased to 110 and then 180. No, you consider it to be separate systems. One system where you are able to maintain it at 103, here you are able to maintain it at 110. It mainly depends upon the rate at which you supply the heat, but the or rather the heat flux. But that's not the only criteria, as you will see when the boiling curve is shown to you. And here it is the transition boiling at 180 degrees Celsius. Here it is film boiling due to very high temperature of the surface. Okay, so now I'll show you the boiling curve, but before that I think I can show you at least one video, because as I just mentioned that this phenomena, let's say you want to talk about the transition, then this is just one still, one photograph, but at the next second it will be different. But so, but still there will be a sizable portion of the surface covered by the vapor, right? So it's not nucleate boiling. Okay, so let me show one of the videos. So here fluid is, or rather water is being boiled in a kettle. So it seems that like there is a kettle and there is a heater in the kettle, and ethanol is filled up in that, and the metal block is at 65 degrees Celsius, right? So you can, in this case you can say that delta TE is 45 degrees Celsius. So here you are not able to see the vapor bubbles, right? In spite of the delta TE existing, but this is natural. This is showing natural convective boiling. So natural convective boiling was not obvious because there was no bubble generated. But when a grid was put behind that, the grid was put behind that, you could see that there is a temperature difference, right? That is, hot water is rising up and the cold water must be going down to take its place. Okay. And if you are able to simulate this or convert it into, like if you're able to measure the temperatures at different points, or maybe kind of uh, videography, which basically based on the temperature, then you can see the temperature difference, and you could see that the hot water was rising in form of kind of plumes, right? That red, this red color here indicates higher temperature. So you can see that the hot fluid is rising. Yeah, yellow shows the moderate and green shows the low temperature, right? So you can see how hot water is rising, right? This is natural convective the boiling that is taking place. So actually it's not real boiling, it's mainly natural convective heat transfer. Though the surface temperature was higher, uh, there was no real boiling taking place. Now if the temperature of the heater is high, then the generation of the bubbles is very clear, right? So now if the temperature is high enough, you can see those vapor pockets getting generated. Yeah, this unstable film, as it is shown, that is transition boiling. You can see how dynamic the phenomena is. And then there is something called critical heat flux and boiling crisis. So we'll talk about that when I show you the boiling curve. Okay. So let me show you the boiling curve now. And what is that it indicate? So on the horizontal axis, you have the excess temperature. This is drawn for water. So typical boiling curve for water at 1 atmospheric pressure. So this is excess temperature. So if it is 1, it means that it is 101, 105, 110 here. So there is a log scale put up here on the horizontal axis, which basically shows the excess temperature of the surface, or rather the temperature difference between the surface and the saturation temperature, that is 100 degree Celsius, right? And on the vertical axis, it is the heat flux. It is the heat flux Q dot boiling watt per meter square. So if you have water as the fluid and if you maintain the surface at temperature between 101 and 105, what you will see, like as you go on increasing that temperature, what you will see is that heat flux is increasing, but that's not very high, right? It's here also it's a log scale, because here you can see 10 raised to 3, 10 raised to 4, 5, and so on. Okay, so this is natural convection boiling, right? So there is hardly any bubble formed, but rather water gets heated up and hot water rises up and gives heat to the cold water, and cold water moves down. So that phenomena is predominant. What you saw in case of that kettle, when the temperature of the heater was 65, you could hardly see any bubbles there, but rather it was natural convective boiling. So that's what will happen when the temperature difference between the surface and the water is not very high, and the heat flux that it can provide you will also not be very high. Okay, so it's hardly somewhere around, let's say it is 8 into 10 raised to 3, so 8 kilowatt or something is the heat flux that is available at 5 degrees Celsius temperature difference. Now, if you are able to maintain your surface beyond that, if you are able to maintain your surface at temperature higher than 105, and this is, let's say, somewhere around 15. So here is point A and point B. So between point A and point B, what you will see that bubbles collapse in the liquid. So bubbles are generated, but they collapse in the liquid. So right, so bubbles are generated, they get detached from the bottom surface and they move up, but their size is not big enough, and because of that they end up giving the heat of condensation to the water body, and they collapse in the liquid itself. Okay. Um, but obviously the evaporation rate at the surface will be very high because because of this heat continuously being added in the liquid pool. Okay. And then beyond point B, that is up to around 30 degrees Celsius, 130 degrees Celsius water temperature. So up from around let's say 12 or 15 degrees Celsius to 30, bubbles are able to rise to the free surface. So they are like they are able to join together and make bigger bubbles and detach from the surface and rise up and rise to the free surface. And you have very high heat fluxes, right? You can see it's even exceeding 10 raised to 6. It means that it can be even more than 1000 kilowatt or 1 megawatt per meter square. It can deliver you such high heat fluxes if you are able to, if you maintain the temperature difference of around 30 degrees Celsius. Okay. So that's a very high heat flux, and obviously the heat transfer coefficient is also very high, which can provide you such high heat fluxes, right? Because basically Q dot is equal to H delta T, right? So so if like at a particular delta T, if Q dot is very high, kind of rising exponentially, then corresponding H value is also very high. So this very turbulent boiling is helping you to provide very high heat transfer rates. Okay, so this whole area or regime is called nucleate boiling. Nucleate boiling. So here you are not covering a very large portion of the hot surface by this bubbles or vapor. So that's nucleate boiling. Um, Now what you see at 30 and beyond that is something unusual, right? It is something unusual. So we'll discuss about that. But let me show some more photographs which will help you understand this nucleate boiling, right? So this is first nucleate boiling and then transition boiling and then film boiling. So here you have different photographs. This is A. This A is showing nucleate boiling, right? So there is a, at bottom there is a rod or heater, and you can see the how bubbles are generated and they rise up in the liquid body. So this is nucleate boiling. This is nucleate boiling, the first part, and that natural convection boiling you could see in the video in of that kettle. Now next thing what you see here, B is beyond point C on the right hand side on the boiling curve. That's transition boiling, and the last one is film boiling. So here this B is transition boiling. Of course, you could see the transition boiling in that video when the temperature of the surface was around 200 degree Celsius, right? So there were large pockets of vapor, and sometimes that area was again occupied by liquid, and that bubble got detached and moved up, but again means liquid took its place, but again there was a large vapor bubble there, and again that got detached and moved up, and so on. So this is transition boiling, which is a very dynamic phenomena. But here a large portion of the heater is covered by vapor. Okay, is like average. If you take average, then still a large portion of the heater is covered by vapor. Okay, so let's go back to the curve. So as I told, if you go beyond 30 degree Celsius temperature, what you could see is something opposite is happening. Though you are increasing the temperature of the liquid, or not liquid, of the surface of the heater, the heat flux has started decreasing. The heat flux has started decreasing, right? Don't connect it with what happened previously. right? Consider each line that you draw here as an independent line, okay, as an independent line. So if you say from the very beginning you are able to maintain it at 40, the your heat flux, or rather let's say 100, the heat flux that you get, that is the surface temperature of the heater is 200, the water is at 100, the heat flux that you are able to get is actually lower than this. So this is peak or critical heat flux, which is as shown here occurs around 30-degree excess temperature. But if your surface is at some temperature higher than that, rather than having higher heat flux, you are actually getting lower heat flux. Okay. What is the reason? The reason is this region is transition boiling. And as I told that in transition boiling, large portion of the heater is covered by the vapor. Now, vapor is not a vapor like air or any gas is a bad heat convector or bad heat conductor or convector, right? So because large portion is covered by vapor, the heat is not that effectively carried away from the heater surface to the to the bubble or to the liquid or to water, right? So because of that, at higher excess temperatures, you rather get lower heat fluxes, because the phenomena or the boiling regime that you are in is transition boiling, and higher the excess temperature actually lower the heat fluxes that you are able to get. And as shown here at around 120 excess temperature, you get the minimum heat flux, and that point is called Leidenfrost point, based on the work done by Leidenfrost. Uh, and at that point actually you see the heat flux, minimum heat flux. So it's a minima, local minima, that you see there. And then again, when your excess temperature starts rising, the heat flux that you are able to get again goes on rising, but this phenomena is film boiling. So by the point you reach here, almost whole heater surface is continuously covered by a vapor film. The generation of vapor, that rate is so high that the before it detaches and goes up, there is already some vapor which is able to take its place. So the heater surface is completely covered by a steady vapor film, and because of that vapor film, here you get the minimum heat flux. Now why does it again start rising? Actually it's not because of the convection or boiling, but this is because of the radiation now contributing more and more to the heat transfer phenomena. So because of the heater temperature now being very high, it is the radiation is also contributing very significantly, and because of the contribution of the radiative heat transfer mode, you are able to again increase the heat fluxes, and higher the temperature you go, higher the heat fluxes you can get, but then there will be a limit to it, because you are using some solid material, metal, and it has got some limitation, right? Because of that, you may not be able to go uh, uh, beyond a certain point, because the metal will start melting. Okay, so this is about the whole boiling curve. And regarding this Leidenfrost point, it was based on the phenomena that was observed by Leidenfrost, and you can actually see this phenomena if you see this dosa making on the hot tawa, right? So once they take out one dosa, and prepare the surface for the next dosa. They sprinkle water on that hot surface. So at that time, what you see is like those water droplets that they falling on the surface of the tawa, they won't immediately convert into vapor, right? They will move around here and there at a very high speed, and only then they will vaporize. So the heat flux is not very high there. Why is the heat flux not very high? Because the temperature is very high. Immediately, the moment the liquid water touches that surface, there is a vapor generated, and that vapor becomes a resistance to the further heat flow from the tawa surface to the remaining liquid. So liquid is able to like retain itself for some time and move around here and there, and then it boils off, right? So that's the leaden frost because the low heat flux is that you get at leaden frost point. Okay, and then the right hand side part is mainly the film boiling. We'll discuss further about this phenomena and further about the boiling in the next lecture. As I told that if you want to do the experiment in the lab and draw this curve, it's not such an easy task. This work was pioneered by a scientist called Nukiyama, and the main contribution has come from him. And what exactly or how exactly he did the experiment, how this full curve can be plotted. So such points will be discussed in the next class.